Hi everyone! Today let's continue. Surfaces. The graph of a three-variable equation is the set of points in the three-dimensional space that satisfy the equation. Usually, this graph is a two-dimensional surface in the space. Let's look at some cylindrical surfaces. So there are three-dimensional equations with a missing variable. Okay, so we have three variables, x, y, z. So in the equation, you can see one of the variable is missing. So a class of the three-dimensional equations that comes up a lot. They are relatively easy to graph, and the functions are missing one or more of the three Cartesian variables x, y, z, such as z equals 2y or x equals to sine z. So these are often called cylinders, even though they are not necessarily the typical circular cylinder that we will probably seen a lot in the previous class, but they are still called cylinder. A trace of a surface is the set of points at which the surface intersects a plane that is parallel to one of the coordinate planes. So let's look at the following example. Graph the set of points in the space satisfy each equation. First, z equals x squared. So you can see here, because the y variable is missing, so this function is actually, we can imagine, is like on the xz plane, right? So we first draw the three axes, x, y, z. And this guy is on the xz plane, so on this plane, right? And z equals x squared, so it's like a parabola, right? And it passed through, we know a parabola passed through 1, 1 and minus 1, 1 and 0, 0. Okay, so it looks like that. Okay, now furthermore, y is a cylinder because the y can be arbitrary number. So that's why we can draw it here. Okay, so and we get something like this. So you can see this is a cylinder. So far so good, everybody. Okay, next, z equals y squared. Well, this guy is on the yz plane, right? So where is the yz plane? So this plane, right? So this plane, and z is a function of y, so imagine this is like the x-axis, this is the y-axis in the xy plane, right? And then this is still a parabola. It passed through 1, 1, minus 1, 1, and 0, 0. So it looks like that. So in this session, I hope you can practice more about how to graph, okay? So, and something like this. So this is the cylinder. Next, y equals x squared. So this is on the xy plane, right? This is the xy plane, and then y is a function of x. So x here. So it passed through 1, 1. It passed through minus 1, 1, and 0, 0. So this is the parabola. And the z can be anything, right? So we draw a picture like that. So far, so good, everybody. All right, let's continue. X squared plus y squared equals 1. This is on the xy plane, right? And it is a circle centered at 0. So we have this guy. This is the circle, okay, centered at the origin with radius 1. And now the z can be anything. So you can see this is like circular cylinder. Okay, x squared minus y squared equals 1. Okay, so this is also on the xy plane. Okay, do you know what is x squared minus y squared look like in the xy plane? It's actually a hyperbola, right? Like this. Okay, and so here is we draw the same thing, so it looks like this and this. Okay, and it is also a cylinder. So let's see here. Okay, oops. All right. Okay, now can you imagine the picture? Yes. Okay, how about this one? This one is a sphere on the YZ plane. YZ plane is here, and then so you know, for the ellipse, we look at the denominator. So this is 4, this is like 1. So 4 is bigger, square root of 4 is 2, so the major axis is on the y. So we have 2 here, the minor axis is 1 on the z. So it is a sphere. Okay, and x can be anything, so so we draw another sphere here. This is what it looks like. So far so good, everybody. Okay, so I want to also show you how to graph the surfaces in the GeoGebra. Okay, so here, the right upper corner, we click View, and then we choose 3D graphic, and then select the graphics. Okay, so let's see. Let's see z equals y squared. Okay. So far so good, everybody. So does it look like what we have here? Let's see. Oh, you know what? This is the red one is the z x-axis. The green one is the y-axis, and the blue one is the z-axis. Okay, so we can move it around, and then you can see this is a parabola, right? And it's parabola cylinder. Okay, let's draw another one. Let's try x squared plus y. Oops. So you have to be careful, go back down and then continue. Otherwise, it will be on the exponent. And then go back down. Just press the right arrow, you can go back down. Oh, okay, I forgot one. Okay, so you can see this is a circular cylinder. And let's do x squared minus y squared and equals 1. Okay, so far so good. This is hyperbola, and then we have a cylinder. All right, and last one, y squared divided by 4, and then plus z squared equals 1. Okay, so what is this? You can see on this side is ellipse, and then we have a cylinder. Okay, so you can play with the GeoGebra and help us to visualize the surfaces and curves in the 3-dimensional space. Okay, let's come back. Quadratic surfaces are described by the general quadratic second-degree equations in three variables. So this is a general form of a second-degree equations. Okay, so we have x squared, y squared, z squared, xy, xz, y, z, and then the lower terms x, y, z, and the constant terms. Okay, so here are the coefficients that are constant, and not all of the second degree terms are 0. Okay, because it's second degree. If you have all of the second degree terms are 0, then it is not a second degree, it's just a plane. Okay, so how to draw those? So here are some types. Okay, so look at this common quadratic surfaces. The first one is the ellipsoid. So ellipsoid, you know, a sphere is like x squared plus y squared plus z squared equals r squared. This is a sphere centered at the origin with radius r. Okay, but if we allow the denominator to have like different constants, then if we just look at, let's say if we hide the z. Oh, okay, so let me see here. So if we hide the z, this is just a sphere. Sorry, this is just an ellipse on the xy plane, right? And so that's why we can look at the traces. So in the plane z equals p, so z equals p is a plane like this. Then when you intersect this surface with the plane, then you get a ellipse, right? So that ellipse corresponds to x squared over a squared plus y squared over b squared equals to a constant. Okay, how about the trace in the plane y equals q? So y equals q, y is a number, then it looks like this. So, and then you can see this is also an ellipse. So the ellipse corresponds to this guy plus this guy equals 1. This guy might be a number, okay, so it might not be 1, it might change. Okay, how about in the plane x equals r? So x equals a constant. This is the plane, and you can see when we intersect it, we also get an ellipse. Okay, so the ellipse corresponds to this, and then this is not 1, maybe some other constants, because when we plug in x equals to r, then you have r squared over a squared, then you move to the other side, it becomes 1 minus r squared over a squared. So this is a new constant. So far so good, everybody. So this is the ellipsoid. So no matter we intersect in the plane like z or y or x directions, we always get an ellipse. Okay, and if the a equals b equals c, then this surface is a sphere. Okay, next, hyperboloid of one sheet. So we have hyperboloid of one sheet and hyperbola of two sheets. So one sheet you can see is connected. Okay, two sheets you can see the two parts, they're not connected. Okay, so let's look at the one sheet. What's the difference? Well, you can see here on the right hand side, this is 1. Okay, make sure one hand side is 1, and then on the left you can see two terms positive, one term is negative. Then it will give us one sheet. So if the right hand side is 1, then if the left hand side one term is positive and then two term is negative, then we will have two sheets. So it depends on, ellipsoid, all the three terms are positive. And then hyperboloid is, you can see some positive, some negative. So one sheet, we have two positive and one negative. Okay. Two sheets, we have one positive and two negative. Okay, so let's look at the chase. So in the plane z equals p, so if we cross it like that, you can see we form an ellipse. Okay, how about in the plane y equals q, so y equals a constant like this, you can see it forms a hyperbola. Okay, so y is a constant, it means we get rid of this. You can see this guy minus this guy is a hyperbola. And when we have z equals a constant, so we get rid of this, well, this guy is an ellipse because it's a plus in the middle. Okay, how about when in the plane x equals r, so x equals a constant, the plane looks like this. When we intersect it, it also gives us an hyperbola. Okay, so in the equation of the surface, two of the variables have positive coefficients and one has negative coefficients. The axis of the surface corresponds to the variable with the negative coefficients. So you can see what does it look like? But so it has an axis, right? This axis is on the z variable. So z variable is the variable with the negative coefficients. Alright, let's continue. So hyperboloid of two sheets. So on the plane, in the plane z equals a number, you can see we get spheres, right? It could be some points that we have no intersection. So that's why it's possible that we have some empty sets. Okay? And then well, why is that? Okay, think about z is a constant. So z is a constant. This is a constant. Well, then it means if we move to the right, we get x squared a squared plus y squared over b squared equals z squared minus over c squared minus 1. Okay, so if this number is big, then we have the left-hand side equals right-hand side is a positive number. So it's an ellipse, right? But if this number is small, this then z squared over c squared minus 1 is negative. Well, these two are bigger or equal to 0. You cannot equal to the negative number, so that's why no solution in that case. Alright, how about in a plane y equals a number? So y equals a number like this. Then we have a hyperbola. Okay, so far so good. Alright, let's see. How about in the plane x equals to a number? So then we get see here, this plane, right? We also, when we intersect it, we also get a hyperbola. Okay, so in the equation of the surface, two of the variables have negative coefficients and one has positive coefficients. The axis of the surface corresponds to the variable with a positive coefficients. So you can see z has positive coefficients. So in two cases, you know, one variable is special. Okay, this guy is special because we have one negative and two positive, right? Then the special one is gonna be where the axis is located. And here, this is positive and the other are negative. So this one is special. Then we also have the axis on that variable. Okay. Okay, and the surface does not intersect the coordinate plane perpendicular to the axis. Right, you can see here, no intersection. Alright, let's continue. Okay, next, elliptic cone. So here, the right-hand side is 0. Okay, so in the plane z equals to a number. Let's see here, like this guy. You can see we form a ellipse. Okay, but it is possible that's on the xy plane. Can you see on the xy plane the intersection is just a single point? okay, which is the origin. So I would see it's an ellipse or a point. Okay, a point is like the xy plane, on the xy plane. You know, xy plane corresponds to the equation z equals 0. Okay, everybody? So let's continue. And then in the plane y equals q, we get a hyperbola. So y equals q like this, we get a hyperbola, right? And in the plane x equals r, we get also a hyperbola. But on the xz plane, so xz plane is right this guy. On this plane, you get a pair of lines that intersect at the origin. So far, so good, everybody? Oh, maybe I should use the green color so then it's more obvious. You can see the two lines intersect at the origin. And on the YZ plane, so, this is XZ plane. We get those two lines. And YZ plane is this. We get those two lines. Okay? So the axis of the surface correspond to the variable with a negative coefficient. Still, this is positive coefficient, this is negative, so this guy is special. The axis is on the special one. The trace in the coordinate planes parallel to the axis are intersecting lines, okay, or a single point. See, xy plane, we get a single point. All right, next one, elliptic paraboloid. Okay, paraboloid. So z equals x squared over a squared plus y squared over b squared. So in the plane z equals a number, see, we get an ellipse. Okay, or those things we have no intersection. Okay, so or empty. And then, we could have 1 point, right? Or 1 point. Okay. So in the plane y equals q, we get a parabola. So let's look at y equals q, then it's a plane like this. See, we get a parabola. And y equals a constant, so we ignore this. This is a parabola, right? Next, x equals a constant, then the plane looks like this. We also get a parabola. And that corresponds to this guy's constant. Z equals y squared over b squared is a parabola, a cylinder, right? Okay, let's continue. Just parabola. Okay, because x is a specific point. Then we get a curve. That's the parabola. The axis of the surface corresponds to the linear variable. So here you can see x and y, they are degree 2, and z is a linear variable. So the linear variable corresponds to the axis of the surface. So far, so good, everybody? Let's continue. Hyperbolic paraboloid. So z equals x squared over a squared minus y squared over b squared. Okay, when z equals a number, so if you intersect a point like this, you get here hyperbola. Or maybe down there, you can see your hyperbola is going different direction. Okay, so here is going this way, but here is going that way. So that is also possible, and so it's a hyperbola. Next, in the plane y equals a number, so this guy, we get what? We get a parabola, right? And by looking at the equation, you can see if z is a positive number, then then we have, let's say if this is 1, then we have a hyperbola. The axis is on the x axis because that is positive. But if z is negative, then we will make it into the standard form. Then the y is the positive term. So the axis is on the y axis. And when y equals a number, then we get a parabola. And when x equals a number, we also get a parabola. Okay, so when x equals a number, we get a parabola. And we'll see if this constant, we get a parabola, and because the leading coefficient is negative, so it's a parabola open down. Okay, and on the y plane, you can see the parabola opens up. Okay, so we can imagine when x, y, or z are constants, and so it's like we find a chase when we intersect the surface with the planes. Okay, so the axis of the surface corresponds to the linear variable. So the linear variable is z in this case. So that's why axis is on the z. So far, so good, everybody. And so here are all the surfaces, most of the kinds. Okay, and so you can also plot some of the surfaces in our like GeoGebra software. Let's just do one example. Okay, how about we do z squared over 4 minus x squared. Oh, see, we already have some nice picture here. Over 2, okay, and minus y squared equals 1. Okay, see, it's a two-sheet hyperboloid. Okay. Alright, so I hope you can like find more examples and try to imagine what they look like. And then you can also use this GeoGebra software to play with the surface and have more idea of about the three-dimensional surfaces. Okay, so that's it for today. Have a nice day. Bye.